So thank you very much for inviting me to speak. It's work we're doing, it's work in progress, which will probably continue to be in progress for a few more years. Probably we're working on the same problem for now about 5 years. And there are different phases of this particular problem. We're throwing almost everything we can on this particular problem because it's relatively large, and I'll show a lot of different things. The people that have worked on this through the years is Lars and Christoph, who are postdocs, and now Mike McMillan, who is a student, and there'll be other people who are working on this particular thing. So I'll speak first about just electromagnetic inverse problems and forward problems. For those of you who have never seen this thing before, it will be kind of an introduction. Then I'll try to explain what do we mean by too large to be solved. So these are really big optimization problems. So we have Michael here. He can probably tell me what I'm doing wrong at the end of the whole thing, and I'll solve this much faster. The next thing I'll try to say, what are we actually doing in order to try to solve these things, and what are we actually working on in order to make it work? And it actually comes with a bunch of different things that need to be combined. So we'll talk about mesh decoupling, multi-scale methods a little bit, stochastic programming a little bit, programming in different languages a little bit. So it will be a little bit of everything, and I'll give some examples and show how you can combine it with some computational aspects of things, and hopefully there'll be something for everyone. Okay, so this is the electromagnetic inverse problem. The typical arrangement is, I don't have a thing, actually. Can you see my mouse? Yeah. So this is going to be a loop that people put current inside the loop, and this current are interacting with. I need to see, this is also difficult, but okay. These currents are interacting with this block, for example, that is inside the Earth over here, and then you can measure data on top of the Earth. So for example, you can measure the data here. Some people drill boreholes, so they measure the data in the borehole. And so let's say this is the data, how the data looks like, and the data can be data in frequency, data in time, so usually it's more than one slice of data. And the goal of the inverse problem is to take this data and to go from here to the block. That's, in a nutshell, what we're trying to do, okay? And if you're looking at these kind of things, the equations that are governing the whole thing are Maxwell's equations. Here we write it as a coupled system of partial differential equation for the electric field E and the magnetic flux B. We assume we know everything besides the conductivity, which is the unknown in the inverse problem. Of course, in the forward problem, you assume you know the conductivity and you are recovering back E. Now, for those of you who've seen Maxwell's equation in a different place, we're neglecting what's called the displacement currents. So we're neglecting, notice this is a differential equation in time over here, but there is no time-dependent part over here. So those of you who are used to see it with the displacement currents, we are ignoring them because we're talking about time scales that are big enough so this can be basically ignored and dropped, okay? So this is the type of things that we're actually solving for the forward problem. For those of you, I know that I put this slide because the University of Washington had a big group of people who were looking at solving this well-known problem, the Dirichlet-Neumann map, when they're looking at trying to recover the conductivity given the potentials. So this is a sister problem. This is the small cousin. So if you actually assume static fields, you can get from Maxwell's equation exactly to here to try to recover the conductivity in a much simpler type of approach. So just to know that these things are related if you ever looked at these things. So what are we going to do to solve this kind of problem? We're going to take the usual path. The usual path is you say, let's discretize the forward problem somehow, and then let's use regularized least squares to solve the inverse problem. Or if you really like to use the statistical framework, you want to look at map estimates. I'm not a big supporter necessarily of that particular thing. I know anyone so far? No, okay. So, I'm not necessarily looking at it statistically. So, but if you want to, there is some equivalence between a map estimate and a regularized least squares. So we're going to take a direction where we're going to always obtain a feasible solution. We'll see in a second what I mean. And we're going to basically build some kind of mechanism to have a priori information and all these usual type of things that you build in an inverse problem. So let's start with the discretization first. So what do we do to discretize the problem? We take the second order system, we reduce it to first order system. Again, I'm not going to show it right now. And then we discretize the first order system just in time using simple finite volume, but the non-simple part comes that it becomes on these kind of meshes. So adaptive mesh refinement locally. And this is what we tend to do with these things. And these are mimetic methods that you can derive for this part of things. They're based originally on methods that were developed by Shashkov and Hyman a long time ago, and we adapted a few things to make them a bit more feasible for our particular problem. Now, when you talk about doing these kind of things, you have to start thinking, how you're going to construct your mesh? And there are two schools of thoughts in here. One is to use a priori estimate of your mesh. So the idea is that I have Maxwell's equation, which I know the Green's function for the, let's say, conductivity, which is going to be homogeneous. And then I can go and say, I know more the field is going to look like more or less. Let's use a mesh which is discretized by that. That's not optimal because the conductivity is clearly not the same as it's supposed to be in a homogeneous space. So people have, for example, came with a post priori estimate where you start with this and then you improve your mesh slowly until you get better and better. Now, this is a great thing when you have to solve a single PDE, but in our context, this is really not very practical, and you'll see in a second why. So we actually work with a priori estimates. And the a priori estimates, we're just basing them on the Green's function. We try to be a little bit conservative, and again, you'll see why, and do these kind of things a priori and come with a reasonable mesh for our problem. So let's say you've done all these kind of things and you discretize all this thing, and you take a differential equation like this, and now you come with a backward Euler method. Remember, this is like a fancy heat equation at the end of the day. There are lots of curls and other things, but it's just a fancy heat equation. And when you do a fancy heat equation, the first thing that comes to your mind is backward Euler, what has come to my mind. So we do a backward Euler step, which kind of looks like that. Or if you write the whole backward Euler system as a big system, it looks like that. So it looks like a block bidiagonal system where this A sits on the diagonal and some other blocks sit on the subdiagonal, which means that if I want to solve this, I have to invert first this guy in order to get the first one. And then, of course, I take the first one, multiply by this one, and solve for the second one. So I zip forward like that, correct? That will be my solution, which is basically what we call time stepping in this particular sense. And this is the way we solve the problem. Interestingly enough, if the time steps are equal, then all these blocks are equal, and that's actually important because, for example, if I decide to use direct methods to solve these problems, then I can factorize this matrix once and use all time steps at the same to solve it for everything the same. If the time steps are changing, then this is a little bit more difficult, and you, for example, want to do something a little bit different. Okay, so when we think about our problems, most problems that we have a number of sources is basically small. So if you think about number of sources where it appears, this source appears over here or over here. So if I have number of sources small, that means if I have one source, I have one system. And if I have, for example, two sources, I have two systems like this, and three, and so on, right? So more sources I have more linear systems to solve. That's basically what it entices to. So more of them have one time, and I need to think about what's the coin I'm going to measure, how complicated thing to do things. And the coin of complexity is going to be number of linear systems I solve. So if I, for example, have nt number of time, ns number of sources, again, forgetting the fact I can store factorizations and stuff like that, the cost is going to solve the kind of problem is going to be number of times times number of sources. That's the basic things. And again, direct methods are especially useful over here because you can actually, you can recycle information. If you're using iterative methods, you want to use iterative method with as much storage that you can that allows you to store information. For example, if you use a ILU with a threshold, it's going to be better than using necessarily an ILU 0 because you can store information and move it between iterations. So things like that are important here. Okay? And a lot of my friends in this business tend to look always on what's the optimal algorithm. So it reminds me all the time that direct methods are not order n, which is what multigrid gives us. And I always claim that this is really not relevant for any real application in many ways because order n, really, I don't care. I mean, nobody here, I hope, would consider solving a one-dimensional problem with multigrid in a three-diagonal system because, well, backslash is working pretty well. So if my backslash in that particular case is mumps, it's also for one-dimensional, you're right. But even for 2D, I mean, for 2D, for example, Helmholtz, you would not try to. So, I mean, again, these are things that they're optimal algorithms, they're practical algorithms, and since this is an industrial application, we opt for the practical algorithm rather than necessarily the optimal one, okay? So let's talk for a second about the inverse problem. This was my 5 minutes on the forward problem and see what we have to do here. So again, we assume we have some we have measurements on electric field or magnetic fluxes, and we want to recover the conductivity. Now we know the problem is ill-posed. We know that we have insufficient data in many cases. We measure only on this surface. We don't measure around it. We don't measure inside it, correct? So insufficient data, and we also know the data is noisy. And then we want to use regularization and minimization. By the way, my favorite question from referees who look at papers is asking, we added noise to the data? And always the idea that noise is really making your problem more difficult. So it's nice to talk to a crowd that have students to tell you that noise makes the problem more simple, not more complicated. For example, if you give me infinite amount of noise, I have an algorithm to compute the solution right now. My m is equal to m0. My solution is equal to whatever I started with. There is nothing I can recover by computation, correct? So the least noise you have, the problem becomes more complicated because there is more stuff to milk from the data. And that's what makes it really more complicated. So show me an algorithm that works with zero noise. It's actually very complicated. It's not so simple as you may think. Okay? So how do we do these things? Well, we have a problem that we're trying to estimate the model by optimization and regularization. So what we do is we minimize a difference between the observed data, which is D here, and QE is the electric field. Q projects the electric field from all the space to where I measure them. And then we have a regularization term that different religions like to add different things. So if you're in the religion of total variation, you have your own thing. And if you're in the religion of L2, you have your own thing. And sparseness have its own thing. And we principally don't care as long as you give something reasonable. So we actually try to develop codes that would allow you to add whatever you think is good for you. Because at the end of the day, no two problems are alike. And for some problems, L1 works the best. For some problems, L2 works the best. Some other things, different things work the best. So trying to be as agnostic as possible what regularization we want to put in, and want to minimize this thing subject to this differential equation that we had before. Okay? If you look at this particular problem, we're trying to look at the reduced space method. So we are assuming that we eliminated the constraints, and partially it relates to memory, partially relates to other practical things. And when we finish eliminating the constraint, we have a reduced or unconstrained optimization problem in this case, where we just want to minimize this. Now remember that every time you see E of m, that means solving a differential equation in time, correct? So that's kind of a lengthy process here that you have to do. And you can compute easily the gradient, and the gradient is actually going to be, for the problem is going to be, well, Q times the gradient of E with respect to m, where you go and you actually compute what it is, the Jacobian, you realize that it's basically some sparse matrix over here which goes from the derivative of the differential equation with respect to the parameter you're looking for times the basically the time stepping matrix inverse. Okay, that's what you really have to compute here. The interesting thing here that when you look at the transpose, or what people call sometimes the adjoint problem, you can see that the time stepping back comes naturally. You don't have to start thinking about the problem in continuous space because the transpose of this means that you first multiply by Q transpose, which remember is just the observation matrix, and then I have to invert that matrix. And to invert it, the natural thing to do is to start from the end and go backward. So if it goes backward, it's equivalent to stepping backward in time, and a lot of these adjoint methods that develop in continuous space doing exactly the same thing. So you're looking at a discrete way to explain why the adjoint is stepping backward in time, which of course in that case gives you the real adjoint of, or the real transpose of the matrix in this particular case. Okay? The important thing to remember from this is that if I'm looking at function and gradient evaluation, that I need two forward problems solved. I mean, one forward, one backward, correct? So that's the cost that I'm paying. If you remember, I'm going to be recording the cost of what I actually have to do, and the cost of function plus gradient, that's going to be two forward problems. Okay? So the minute I have a function and a gradient, I can start thinking about optimization. So for example, people can think about steepest descent, okay, maybe. Then you want to think about, let's do more complicated stuff, nonlinear conjugate gradient, maybe limited memory BFGS. And of course, the advantage of these methods is that you just have to compute one forward, one adjoint for every step, so you can easily do it. The storage is actually great on these things. One of the reasons that you don't necessarily, if you have multiple sources, you can do it one at a time. So the storage is much great, but in our experience, these are not converging fast enough. The convergence of these things tend to be very slow, and sometimes it just doesn't want to go anywhere. That's our experience. And although people right now in the institutional machine learning world are especially obsessed with first order methods, we are still apparently not there, and we like second order methods. They seem to work much better for us, at least in our experience. And what you have to do is you really are looking at the Gauss-Newton approximation, where you have to remember again that every time I apply this times a vector, I pay for a forward problem, and this time apply for the adjoint problem. Now, of course, I'm not going to store the j. I'm going to use the fact that I know what j times a vector is, and I'm going to use a conjugate gradient on top of this thing in order to try to solve this with inexact or with CG. So we're looking at some kind of an inexact Gauss-Newton method where this is solved by conjugate gradient to a very low accuracy and continuing on. Okay? So this is basically what we're doing. Okay, that's the whole field in a nutshell. This was what we've done a long time ago as well, and now I want to do some kind of cost analysis to myself to see what can I actually solve. So again, the currency is a number of solver for the linear systems. So that's my currency, and again, any gradient or every forward problem with a gradient I have to solve. So it's here. It's 2 times number of sources times number of times, correct? So if I solve a problem with 50 time steps and have 2 sources, just to compute forward problem and adjoint problem, I'm already with 100 linear solvers, right? That's already what I have here. Now, if I look at if I do Gauss-Newton method with conjugate gradient iteration as the inner solve there, then what do I have here? Number of times, number of sources, number of conjugate gradient iterations, right? Times number of Gauss-Newton times 2, because for conjugate gradient it's forward and adjoint for each one of them. Okay, so I take this number and I want to see what is going to cost me to solve a typical problem. So let's say I have 2 or 3 sources, so that's kind of a typical problem that people have done. 50 Gauss-Newton iteration, 5 PCG iteration, you calculate, you put it there, you have 60,000 problems. And you say, okay, 60,000 problems in today's technology, if I use adaptive mesh, I can solve this in a few hours, maybe a day or 2. Okay, so that's reasonable. That's 2 or 3 sources. The cost, if I'm using direct methods, no cost for preconditioner, correct? There is a preconditioner on the Gauss-Newton system, but that's cheap, relatively speaking. Yes, but this is PCG on this guy, correct? And the PCG for the cost of preconditioner here, I'm cheating a little bit, but it's actually, well, for some problems it's cheap. You are preconditioning with this guy, which is sparse matrix, correct? Yeah, so it's. But to be completely honest, in the second, one of the problems, the kind of half-open problems we have is that, and I'll talk about it at the end, but for the problems we're solving right now, this is actually the most expensive operation we have. Like inverting this guy is the most expensive operation we have. And I'll say something about it. I hope I remember to say something about it. Okay, so now the movie's supposed to start. So this is a movie, and it's a movie that I, of course, stole from YouTube. This is this company that sometimes give us data, and this company is flying airborne electromagnetic surveys. So remember I showed you in the beginning there was a loop on the ground, and maybe I moved this loop once or twice or 3 times, and every time I move it, I measure data. This thing is a little bit different. I'm supposed to be starting. I'm hoping it's starting. I don't know. One of the things. Yeah. I'll start describing what it is, and maybe it will come. So, and if not, you'll have to live with my description. Should have been there. So there is basically a loop, but the only difference in the loop is in the beginning it's on the ground, but then there is a helicopter that actually lifts this loop off the ground. And by the time the helicopter lifts this off the ground and starts moving it along the ground, it's making some measurements. I need to press? Yes, apparently I need to press again. So it starts making measurements. Okay, so this thing is a flying loop. It's not a loop that is standing in one place, it's flying. And as it's flying, it's measuring. So if before I had my description of a loop that measured 2 or 3 times, now this thing is measuring continuously, or basically every few, so this is the loop. There is a person here, just to put things in perspective of what the size of this thing, you'll see the person in a second. So to see this is pretty big. And yeah, that's kind of the place that it moves to. And now, that's what happening. And now it's going to start flying. And again, as it's flying, it's measuring, let's say, every 50 meters. Okay, that's kind of a standard thing. And you can see that, unlike our usual thing that we like to assume that the Earth is flat, it's not so flat in here. So something have to be modeled like topography, if you want it to be useful. These are things that needs to be really taken into consideration to make this thing work. Okay. So now, if I look at this, the number of sources will be somewhere around 1 million. Well, we're not there yet in terms of solving 1 million problems, although I think our code can if we just give large enough platform, but at least 100,000 systems, linear systems, is really the case. It covers a very big area. So for example, there is a survey like this right now that was done and the data is public, which is over about big parts of British Columbia. Okay, so you have area of 200 by 100 kilometers, and you want to discretize it. And here I use the number 10 meters, I think, for the discretization, which some people say that's what you need in order to be geologically interesting for them. So if you have an area of 200 kilometers by 100 kilometers by, 2 kilometers deep, and you want to look at this in 10-meter resolution, you can start to think what size of problems you're actually looking at. And of course, as I show you, non-trivial topography, and sometimes there are non-trivial geology. So sometimes there are faults, there are lakes, there are salt bodies. We're close to the water here. So These salt bodies are very conductive. All these things need to be taken somehow into consideration when you're doing your thing. Okay? So I go to the same calculation I've done before. All this thing is exactly the same. The only thing I replace it is that I put a million sources in, and I go and I see that there's over 10 to the 10 linear solvers I need to do, and I start scratching my head, and I realize that this is not going to be happening today, correct? So this is where we were about 5-6 years ago when we realized that we want to solve these kind of problems, and this is difficult, okay? So again, I mean, what do we do? I mean, there's a do-nothing approach. The other approach is to say, let's try to solve it by combining different technologies from different places. So whatever we can, we're going to utilize here. And first thing we need to make, if the linear systems are large, let's try to make them smaller. That's the first thing to try to do. So if I can make them smaller, of course I can solve any linear system faster. The second thing is I want to reduce the number of linear systems that I have to do this somehow, and this has come by stochastic programming. And the last thing, of course, I need some kind of parallel system. I cannot, not four processors like I have on this machine, but something a little bit larger, which is important to do. So let's go with the first idea of mesh decoupling. So mesh decoupling is a very simple idea. So let's say this is the half of British Columbia I'm talking about, a slice of half of British Columbia. And let's say that every blue dot here is a place that I run a forward problem. Now, we're lucky in the sense that our forward problems are elliptic and parabolic, if you want to think about it. So we don't have a hyperbolic problem, which means that things are decaying, correct? So if I'm measuring stuff over here, whatever happens here is probably not so relevant, unless it's a huge body, right? So I can start designing meshes that will be local for each source. So each source will have its own mesh. Okay, so where the mesh is going to be local next to that source, and is going to go further away, and is going to actually be here very, very coarse, and here is going to be very fine. So that's the first thing we can do to make the problem tractable on this particular mesh. This is maybe going back to the a priori versus post priori error estimates. When we teach, at least when I teach numerical PDs and I tell students to mesh the problem, we tell them, you mesh the problem, then you solve the thing, then you look at the solution. If it doesn't make any sense, maybe you want to do more mesh points in certain areas, and you want to look maybe at gradients of your solutions. Well, again, I have something like 50,000 meshes. I'm not going to look at every one of them. I need to have some automatic way to do this. If I solve things more than once, it could be a problem. So that's why the a priori estimates here of the mesh is really important, because if I need to start remeshing things for these kind of number of sources, that's, again, not going to be pleasant here. Okay, when you work with Christoph, who has worked on this as a postdoc, you realize that Christoph doesn't take anything in granted, and he asked immediately how many sources should we put on every mesh, and he did a study when eventually we concluded that actually putting one source on a mesh, so doing an individualized source, pays the best for this particular thing. Okay, so I'm going to go over this. It's not that important in the end. The second question, which is actually a bit more interesting question, is this. So let's say that I have my inverse mesh. Remember, inverse mesh is fine almost everywhere. And now I have my forward mesh, which is only fine in a few things. So you can think about, I want to model my loop to be over here. And let's say that the anomalies that I have looks like this. So this is topography. I mean, this stuff is even less interesting than this. There is a mountain here. And my mesh is such that it's going to be very fine in here, but it's very coarse in here. Okay? So what does it mean? It means that I model this whole cell here as one conductivity. But clearly there is air here, which is like 10 to the minus 8 in Vancouver on a rainy day. And this thing is like 10 to the minus 2. So there's 6 orders of magnitude, and I'm averaging this somehow. So what should I do? How should I average this thing? And we worked quite hard to think about what different type of averaging. And what we actually start looking at, we start looking at multi-scale finite element methods, which are actually very similar to those of you who've done operator-induced multigrid interpolation. And people who have worked on this extensively were people that are looking at petroleum engineering, so especially Hamdi Chalapi and Jenny looked at this quite seriously, and we applied it recently to Maxwell's equation. The similar work applied to Maxwell's equation. We're now in the studies, does it really pay off compared to, for example, logarithmic averaging, which seems to be another way to do these kind of things simply. Okay? At the end of the day, you can think about, again, coming with an interpolation matrix that is this capital P here, which depends on the conductivity if it's operator-induced. And now you have a smaller system which solves for EH, where you're doing the usual P transpose AP in order to relax the problem. So if you boil down what these kind of techniques are, multi-scale finite elements techniques are, they're just this. They're not more magical than this, and the big magic is building that particular matrix, which I'm not going to go over right now. So assuming I make my problem small enough, I can solve now problems relatively quickly. And I say relatively quickly, we solve now forward problems in much less than a second, for example, for this particular thing, with all the time stepping and everything else. But we still have a lot of them, right? So how do we going to reduce the number of forward problems we're solving? And also there's issue in storage. If we want to do Gauss-Newton, what I kind of neglected to say, but you have to have all the fields stored as well. So what do you do with storage? That's another thing. So here we looked at what people in machine learning are doing a little bit. And if you think about it, our forward problem is done by basically summing over all these sources. And there is some kind of, I mean, this can be a row, so row can be a square in the simplest way, or it can be anything else. Again, there's any kind of problem you want to have here. And which, of course, the gradient is also a sum, and the Hessian is also a sum. So that's kind of an obvious thing to look at. And then the first thing you say, I mean, at least for the Hessian, why the hell do I have to do all of them? I can just pick a part of them. And this is an idea that was originated, I guess, by Nocedal and Bird, that you just say, let's take a subset of what I have here and to sample the Hessian. That's an obvious idea in a sense, because we all know that for inexact Newton method, nobody requires to have the Hessian exactly. So that's something that is important. But you know, for this particular problem, it actually makes a big dent in storage, because it allows you to store much less information. Because again, for these guys, you have to store something in order to apply them. So it allows you to apply much less storage. The calculation is not so bad compared to the storage problem that it saves you. You can go a little bit more wild, and you can say, why do I have to compute everything? I can, for example, not take the gradient over all the sources, but take only a subset of my sources and approximate this as my gradient, rather than on everything. And a lot of people have done work on this. There are apparently some new algorithms in the market for machine learning that are claiming that, so the problem, by the way, all these algorithms that work in here, they exhibit some kind of a sublinear convergence. Luckily, we don't really need to be in the sublinear region. We usually do a few iterations and we have to stop before we get to that very, very long tail of things that don't converge. To understand exactly what it means for us, I don't really know. I mean, these kind of methods, they're very difficult to actually see what exactly they do for you. But it turns out there are new customers, or there are new things right now that are suggesting that linear convergence may be achievable. But it's not really clear this linear convergence is not linear convergence with a constant of 0.9999. So right now all these methods are not so clear how well they apply. In practice, these things tend to work very well when the sample size is reasonable for this. Again, if you look at other problems like full waveform inversion, which have been recently, there's a set of algorithms which are working very similar to that. Again, I don't really have a strong opinion right now on this. I think that in some problems we see very slow convergence, especially if you do the sampling not in a smart way. I'll get back to this. So let me talk a bit about a few issues on the stochastic programming. So for example, let's take this as an example. So think about this as, again, a three-dimensional thing. This is the surface. This is in depth. And the goal of this survey would be to find, of course, these bodies. These bodies are, I think they call massive sulfides. They're supposed to be ore, basically. Now, if I do just random sampling, so if I do sample everywhere here, and I would not sample close to these things, I'm just not going to see it. I mean, I'm just going to miss it altogether. So just doing stochastic sampling, I may get the long frequency structure of what I'm trying to find, but the short scale structure that I'm actually trying to really find, so what people really care about, I'm going to miss. So if you're not going to do anything which involve with some kind of stochastic sampling, or some kind, preference sampling, so you say, I want to sample in some places more than others, you may miss the whole thing altogether. And I may show you something about this in a second. So one of the things that we have done is changing the sampling to look at the data and come with sampling based on the data. And remembering that what we actually have to do here, if you think about the sampling, the misfit is just an integral. You can think about it as an integral, which you're replacing with a sum, and then try to see that the integral is well represented of what you're doing, not just to say we're just sampling randomly because the algorithm does it randomly in some way. So we've done some work on that to see that things are doing a little bit better. So let me give our first example with doing all these kind of things. And this is, people call it a toy example, but I think that most of you will agree that this toy is not such a small toy. So there is this model, which is called the Noranda model, which some companies came up together and gave us. And the nice thing about this model is that it's semi-realistic. It's three-dimensional. This is a slice through this. There is what they call real geology, and they have some geological units that I don't even know how to pronounce their names. And they assume they've done this survey, for example, on here, when you can actually go and start simulating what you do. So you'll see what you actually can see in a real in a real scenario. That's what the goal of this thing is. Okay, so this is the system specification. There's a lot of things here that doesn't necessarily make sense, but for people who are not in this business. But the important thing is that there's 1,024 sources here, transmitters here, and 19 time channels. So it's not a small problem. I mean, it's not something. I mean, this is what we consider a toy problem, and this is not a small problem. Okay? This is the true things, and this is what we can recover for this particular model. And you can see that the long length wave scale is actually fine. When you start talking about what's really interesting, the short wave scale, again, this is the true thing, and this is what happens when you're using stochastic algorithm with importance sampling. So you actually make sure you sample where things are actually changing and there is action. And this is what happens when you sample randomly. You miss the target. So again, you maybe recover the long offset or the long scale frequency in the data, but you did not recover the small targets, which eventually, this is why people fly these surveys. I mean, they pay millions of dollars to fly these surveys in a hope to find this. So if you have an algorithm that doesn't find this is not really nice. I'm going to quit this to go over this. This is a real example, but I want to go over other things. So this is a real example that was real. This is real data that was given to us, and people actually solved this. And I want to move to work what we have done recently on high contrast targets. So these inversions work relatively well when the problem have this kind of smooth and a little bit of maybe stuff that looks like that. But we had a bunch of cases. This is a real data example that there is a dike. So dike basically is a very conductive thin plate, you can think about it, that's dipping in a certain direction. Okay? And there can be a lot of them in a data set. So this data set, the people who look at this and know how to interpret it, and that's not me, look at this and say, okay, there is 1 and 2. And by the way, this is only one time slice, or one frequency slice. So you can think there are many, many of them that they're giving to us. And they say, okay, there's 1 and 2. And if you run your regular algorithm, it smooths this whole thing out and doesn't really give you anything which is kind of interesting or what you really want to try to get. So the way we try to approach this problem is to try to divide the model into two, to a smooth part and a sharp part. Right? And with the sharp part, we're going to try to use a level set method to find it, but we're trying to use a parametric level set method to find it, which I'll show you in a second what it means. And the smooth part, we're going to do exactly what we've done before. So we're going to try to differentiate these different scales that we have in the model. Again, the long, nice, smooth scale, and the short scale, which is really kind of the dike part. And one way to think about this thing is to think about, okay, let's take our level set function and build it from some small other function, and the functions are going to be something which looks like that. So this is going to be the center of something minus this thing which is basically giving you some kind of an ellipsoid. So when you apply a Heaviside function to it, you get something which looks like that. Right? So if I now can replace my parameters that I'm going to find, they're going to be the location of the center. So these are 3 parameters here, and since this is a symmetric matrix, another 6 parameters to represent this. Right? So that's what I have to find instead of and that will give me my parameters to find. So you can actually make it, and this is well known. By the way, all this work is I should say, is based on work by Misha Kilmer and her colleagues. She've done this work in many years. Recently, they published a very nice paper that summarized these things, where you can combine different number of these kind of bodies, and you get really nice results from this. And our experience was that it's very robust compared to, let's say, the regular level sets that were also working for us, but not as robustly as this. And of course, you can generate more than one level set if you just start making products of these things. The only thing you have to be careful is that if you start having you add a lot of these things, the problem goes back to be ill-posed and everything. All the bad things starts to happen again. So how many of them to put and how to put them in the right place and all these kind of things, that's a little bit of an art part of the whole thing. But again, it seems that the art part is not that bad, at least for the application that we run over here. So let me just show you what we have done in synthetic studies and then in real data studies. So this is a synthetic study where you are going and you're taking basically 3 dikes in this case, and you're representing. So this is again a slice from the top, so the XY direction, this is an XZ direction, and you try to recover this. And you see that you have a pretty good recovery. Now the bottom is not well recovered, but that's not really surprising because these surveys are sensitive more to the top than to the bottom. We're measuring from the top, correct? So recovering things on the bottom is usually very questionable. Every time you see something here, you kind of realize that it's not necessarily real. It's some artifact of the algorithm. But you can recover these relatively thin dikes relatively well with the right angle, which is what's important in the application for people. we applied, this is, by the way, this is the data fit. So whenever somebody shows you an inverse problem talk, ask to see the data fit. This is where you know if they cheat or not. So if it doesn't fit the data, they got a very nice picture, but yeah, it doesn't necessarily say much. So we'd like to show the data fit that is predicted and observed, and and to see that every time curve. So each one of them, each data here have a time decay channel that involved with this. So this is one of them. Shows you do a pretty decent prediction of the whole thing. So this is a realistic example, and I show only the rough part. The smooth part, actually, I couldn't find a slide for this, which was annoying because I have a smooth plus chart. But this was done with a real company, which is in Vancouver, actually, that gave the data. And you can recover these very thin targets, and they're actually either drilled on it or drilling on it, which has always caused me to be a little bit more suspicious. But they're going to actually verify this in drilling. I believe it was either this summer or next summer. I don't know what the thing is. But this is the type of results. I mean, you can get really thin conductors out of these things by putting this information in. Okay. So I want to talk for 2 minutes about implementation, because I have, I think, 2 or 3 minutes. And we actually moving in the process of moving everything to Julia. So how many of you heard about Julia? How many of you didn't hear about it? Okay, now it's not fair. Everybody who didn't hear, they say, okay. So Julia is a new language or a new computational language, which is, I find it to be very nice, although there is some things to work on. And I just want to think about for a second, what's the process for us basically from nothing to some algorithm that does something. Well, typically what happens, somebody in the field have some idea of doing something. It could be in the geophysical field or in the medical field. So somebody have a new way to collect data or to do something. Then we come up with a mathematical model. You see, this guy was very serious about his mathematical model. And then we take this mathematical model, and somebody like me sits in front of a board and have a great idea for an algorithm. Then we code it, and it used to be for us MATLAB. And so you code this thing somehow. And then you run your stuff and you visualize this thing, and you really hope that the visualization makes some kind of sense to you. Otherwise, you have to go back to either here, or sometimes here to see where the problem was. Correct? That's usually where things are. So, by the way, the worst case, you visualize and you realize that the guys in the field have done the worst experiment possible that they could have done, and they should go back and do the experiment again. It happens as well, but let's hope that they've been smart enough. So it used to be for us that this step over here, or from here to here, was a MATLAB step, and I think probably, I would guess that most of the people in this auditorium are doing the same thing. The problem is that when you finish with your MATLAB code in a paper and you want to go to some more industrial application, or if you want to work with parallel computing, MATLAB is really not the answer today. And MATLAB does not really have parallel computing capabilities that are any reasonable. And MathWorks are not really coming up with a computational model or paying model that we can actually work on a computational platform without paying them an excessive amount of money. Because every time you need a new license, you need a new, for a new machine, you need a new license. And until they realize it, they're going to have people, I believe the people who do parallel computing will start dropping them, which is essentially what happened to us. The second thing is that Julia is allowing you to do things like for loops, allows you to define variables. You can do sloppy work like MATLAB. I don't care what the variable is, but I can actually say that it's an int 8 or an int 64, or I can basically go to the Fortran level. I can use things on BLAS, on sparse BLAS. So for example, when we do y is equal a times x in MATLAB, we allocate space for y. We don't do it like we used to do it, when we have space allocated for y first, and then every time we redo it, it's already allocated. So if you actually look, for example, at the implementation of conjugate gradient in MATLAB, it's expensive not because the matrix vector products, they're actually very efficient, but it's the allocation, deallocation that takes time. And you can bypass all these things in Julia, which is very, very nice. Okay? It's not that this is only, I mean, there are some disadvantages. It's a language in the making, so there is a lot of issues. But it's very nice. It's almost as easy as playing with MATLAB on one hand. On the other hand, it does allow you to have the flexibility that languages like C or Fortran or other things have. So I think it's a good compromise. We're from Canada now. It's a very compromising country. So we like this thing. Okay. I think my time is up, so I'll get to the conclusions. So I think that, again, I mean, this is one of these, this problem is one of the most challenging inverse problems, at least I've seen, in terms of the cost and the different tools you have to apply to this. I think the thing that, again, helped us solving it was reducing the size of every forward problem, the size of the linear systems, reducing the number of linear systems with stochastic programming, and I think the most, again, and the interesting thing is developing software for this, and the question is, can can we do it again more efficiently? Right now we have a software that is actually being used by the industry. I mean, these examples that I showed you were actually delivered to the industry last week. So a few mining companies that are funding us are getting this software, and they're actually hopefully using this software to get some results. Okay,
Any questions?
I was curious, for your forward problems, when you show the adaptive meshes, what's driving this? I mean, is this your expert experience, or you actually, what's the, but you did have an Opposite or an error estimate, yeah?
yeah, we have a Green's function, correct? So these problems, when you know the solution on, there are actually a bunch of different Green's function, but you know the Green's function in continuous space, and even on a half space, you know the Green's function. There's an analytical expression for this. So you take the Green's function, and you just put more points where the Green's function is decaying. It decays like 1/r square, for example, in that case. It's kind of like a Laplacian. So you know what to do there.